Welcome to This Explainer. Today, we're diving straight into a high-level masterclass on the critical, frankly fascinating engineering systems that literally save our cities from ecological collapse. As our urban populations just absolutely explode, the invisible infrastructure beneath our feet is being pushed way past its absolute limits. So today, we aren't just going to gawk at the problem. We're going to anatomically deconstruct the incredible, mathematically precise engineering solutions that are designed to process all our waste sustainably. Let's dive right in. Think about the stark contrast between the past and the present for a second. Historically, we had these pristine waterways navigating seamlessly through communities, a perfectly balanced ecosystem. But today, we've got modern urban canals so severely choked with industrial and civic waste that it takes heavy excavators just to scrape the surface clear. This is exactly what happens when basic biological carrying capacities are completely ignored. And the consequences are far, far more severe than just some floating garbage. What you're seeing is not a controlled burn. This is Bellendor Lake. The water here is so deeply saturated with untreated pollutants, complex organics, and volatile chemicals that it literally catches fire. I mean, when water actually burns, that is the ultimate undeniable failure of urban environmental engineering. To solve this crisis, we've got a clear agenda today. First, we'll look at the untreated wastewater crisis. Second, today's learning objectives. Then, we'll break down three major systems: the upflow anaerobic sludge blanket, vertical flow constructed wetlands, and natural treatment lagoons, before we wrap it all up with a summary and future outlook. Section 1. The untreated wastewater crisis. When ecological balance fails, the consequences literally spill right out into the streets. Imagine being forced to navigate through massive, snow-like froth just to go about your daily commute. But it isn't snow. This foam is the result of untreated surfactants, phosphates, and industrial discharge violently churning together. It is a massive public health hazard masquerading as a weird weather event. And superficial fixes? They inevitably fail. Simply throwing up a physical wire mesh at an outlet proved to be a completely failed, short-term engineering miscalculation. A physical barrier does absolutely nothing to treat the underlying volatile chemistry of the water. It just allows the toxic froth to overflow, cross the mesh, and inevitably ignite, like it did at the Yamlaker outlet. You simply cannot fence in a chemical reaction. You have to engineer a biological solution. Section 2. Today's learning objectives. So having met our prerequisite, which is really just grasping the absolute, non-negotiable necessity of intervention, here's what you're going to get out of this session. By the end of this explainer, you'll transition from merely observing the problem to actually mastering the step-by-step technical requirements behind high-tech biological reactors. We'll deconstruct the hidden layers of nature-based wetlands, and you'll completely understand the brilliant symbiotic ecosystem loops that drive natural treatment lagoons. Section 3. The upflow anaerobic sludge blanket. The UASB is just a brilliant feat of biochemical engineering. Honestly, think of it as a giant, highly controlled stomach for the entire city. It utilizes very specific anaerobic bacteria, meaning they thrive without oxygen. As the wastewater flows from the bottom up, these microbes get to work. They simultaneously clean the water by digesting all those organic pollutants, and, as a byproduct, they excrete usable energy in the form of biogas. To really ground our understanding, let's contrast the massive external physical scale of these tanks with their precise internal mechanics. The untreated water, or influent, is forced in at the bottom. It rises through a dense, suspended bed of sludge granules. As that biological digestion kicks in, gas bubbles start to rise and hit these cleverly angled physical baffles at the top. These baffles are absolutely critical. They act like a three-phase separator, physically dividing the rising biogas, the solid sludge, and the treated liquid effluent so they can all be routed perfectly. Notice how perfectly ordered this internal environment is compared to those chaotic, burning lakes we saw earlier. The granular sludge acts as an incredibly efficient, active biological filter. It sends precious combustible biogas straight up through the central vent to be collected, while the clean effluent safely and passively exits the system from the side. It's a closed, highly efficient loop that turns a massive problem into power. Section 4. Vertical flow constructed wetlands. Now, at first glance, you might walk right past one of these, thinking it's just a dense, beautiful field of tall grass. But it's actually a highly sophisticated, biologically balanced treatment facility. The distribution pipes at the edge are the giveaway here. This is a constructed wetland, where completely natural botany and incredibly precise civil engineering meet to quietly and very efficiently scrub urban wastewater. Beneath that pretty surface lies a carefully calculated stratification. You've got wetland plants, technically known as macrophytes, sitting atop very distinct engineered layers of sand and gravel. And crucially, sitting right beneath all of it is an impermeable liner. That liner is there to guarantee we protect the natural groundwater below from any cross-contamination. Let's actually track the exact physical journey of a single drop of water going through this system. First, the dirty influent is spread evenly across the surface through those distribution pipes. Then, gravity takes over. The water percolates straight down, passing through the dense macrophyte root systems and the granular layers of sand and gravel. These layers act as physical traps for suspended solids and biological habitats for cleansing bacteria. Finally, the cleaned water hits the bottom drainage pipe. And notice the engineering precision here. That pipe sits on an exact 1% slope, specifically calculated and graded to ensure perfect passive gravity flow without waterlogging the roots above. Section 5. Natural treatment lagoons. Now, a lagoon is absolutely not just a pond. It is a carefully dimensioned, precisely engineered open-air reactor. It utilizes entirely free natural resources, the mechanical mixing action of the wind, and the radiant energy of sunlight to drive some really complex biochemical reactions. Notice how the water column itself is strictly divided by function into two distinct layers. You've got an oxygen-rich aerobic zone up top and an oxygen-deprived anaerobic zone down below. Here is where the magic happens, and it's all about a continuous, mathematically elegant, symbiotic loop. The sunlight powers the algae, kicking off photosynthesis to create dissolved oxygen, right? Then, specific bacteria take that oxygen and aggressively use it to break down the complex polluting organics into simple inorganics and CO2. And what happens to that CO2? Well, the algae consume it to grow, continuing the entire cycle all over again. Meanwhile, gravity just pulls the heavier, inert waste particles straight down to that anaerobic layer where they safely settle out as detritus. It is literally nature's own perpetual cleaning engine guided by human engineering. Section 6. Summary and Future Outlook. So, comparing the three distinct solutions we've mastered today, we see some really clear strategic differences. First, the UASB leverages high-rate anaerobic digestion, and its key byproduct is actually usable, combustible biogas, literally turning city waste into a power source. Then we have constructed wetlands, which use vertical biofiltration to give us beautifully clean effluent while maintaining a lush, natural aesthetic for the community. And finally, lagoons, relying on the incredible aerobic and anaerobic symbiosis of algae and bacteria to give us a brilliantly low-energy solution driven entirely by free sunlight and wind. As we wrap up this explainer, I really want to leave you with a highly practical question to think about. Consider the infrastructure around you right now. How is your local municipality balancing their rapid urban growth with the critical, non-negotiable need for sustainable wastewater ecosystems right beneath your feet? Are the systems hidden beneath your own streets scientifically capable of preventing the next Bellender Lake, or is it urgently time for an engineering upgrade? Thank you so much for joining me in this masterclass. Keep asking those tough questions, and I'll catch you in the next one.